Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where we talk about everything I want to, science and math. And today we're going to be talking about physics, static electricity. So there's two kinds of electricity, static, and which means still, and current electricity, electric currents. But static electricity is a little bit confusing. Because if I tell you that a body of water is static, then you imagine a lake that isn't moving. And if I told you that, if you had a body of water that's moving, you'd imagine a river that's moving in a current. And that's a little bit right. But the thing is, the static electricity builds up and moves. So that's what lightning is. That's what, when you get zapped, when you're walking in the winter across the carpet in your socks and you touch the doorknob. We used to have a sofa that every time you would push down on it to stand up, the coils in there would shock you in the wintertime. A friend had given it to me. It was a really nice sofa, but it kind of hurt. It was a little bit painful. So static electricity, there's a couple of different things about static electricity. One is it really starts going back to the Greeks. A lot of our science really goes back to the Greeks. Like Democritus was a Greek scientist who gave us the word atoms. And same thing with electricity. Greeks had noticed that amber, from Jurassic Park, that if it was rubbed with certain things, it would produce static electricity. It could shock you. So they named it the word that we get electron, electro, electricity from. And it goes back to amber because they did experiments with electricity and amber going back to the Greeks. But remember then, for a long time in science, nothing much happened until the 1700s. And that's what happened with the study of electricity too. It was Benjamin Franklin, the patriot on the money. He's on the 100, right? $100 bill, I think, yes. My child is saying yes. But anyway, he was more than a political person. He was a scientist, and he did some of the first scientific studies, and he was a famous scientist before he was a famous politician with electricity. And he, of course, he's known for the kite experiment, but he was doing experiments before that with electricity. What he was really working is he was able to show that the static electricity that comes from socks in the wintertime and the electricity that in the cloud is the same thing. And so he's the one who gave us that negative and positive for electricity, and we say that electrons are negative. We could have said it the other way around, but we think of electrons as positive, and the nucleus of an atom is positive and electrons negative. So rubbing the atom, positive and negative, we talked about that. Okay, so this also intersects a lot with chemistry, and usually you've had chemistry before you take physics. And that was another thing I was going to tell you guys, is we are not doing this whole book. The last part of the book is all chemistry stuff that you have probably already had. And some of the other chapters, we're going to be skipping some, or really more of an AP Chem or AP Physics or college physics level. So if you want to go further than this class does, go for it. You can read the chapters. You own the book. You can read the chapters and find YouTube videos to explain every bit of this. I've been watching a YouTube channel. It's called The Physics Girl, I think. But it's a girl who goes around and explains stuff in physics. They're really good videos and interesting. So there is plenty of videos out there if you want to learn everything in this book. Go for it. It will take you probably longer than the school year this year. You'll probably have to go over the summer or pick it back up next year, but why not? If you did learn this entire book, you would be better prepared for college physics, and you would probably already know everything that they're going to teach you in college physics. Because this book is a pretty high level. This is not the regular physics I used to teach regular physics in public school decades ago. We won't talk about how many. And this book certainly goes way deeper in those concepts than the regular physics I taught. It's much more of an honors level book. And at the level I'm doing it, and it's got a lot more in it that I didn't learn till college physics. So some of that I'm just sort of skipping for you guys because I feel like I don't want you to be frustrated. I want you to love physics because science is great. All right, so back to electricity. This is part that overlaps what you learned in chemistry. If you remember chemistry, it was J.J. Thomson who started discovering, first you had Ben Franklin in the electrons and electricity, and then J.J. Thomson came along and he figured out that the atom is electrically neutral, but it must have a negative part to it, because this is a situation where technology got ahead of the science and they had made a ray gun. How cool is that? And so what do you do when you make a gun? You shoot stuff with it. You do experiments with it, right? So that if they have their ray gun shooting, they figured out that they could make the ray scoot or be attracted or go straight. So they realized that the atom must have, they already knew that opposites attract and likes repel. And so they knew that there must be a negative part to this atom because of how this ray interacted. So J.J. Thomson came up with the model of the atom called the plum pudding model. You can tell this was a long time ago because that's not a popular dessert anymore, but it was back then. And he thought it was like positive goo with negative little like raisins in it or plums. Now, actually, it was the British idea of pudding, and you know their pudding is that they use the word pudding for dessert, and so a plum pudding was really sort of like a round cake with plums in it. So that would work with the Dalton view of the atom, that the atom is like a round billiard ball. But anyway, so that's what he thought of, so that it would be neutral. Well, his friend Ernest Rutherford did an experiment to prove that J.J. Thomson was right. He got gold foil, he shot it with their ray gun that they had, and what he expected to see on this glow-in-the-dark wall that would flash when the rays hit it was a big old splat, because if you shot pudding, you would get a big splat on the wall. Instead, they got the rays went through straight, hitting the same place over and over and over again, 99.9% of the time, and every now and then it would be deflected and even come straight back at him. Rutherford said he couldn't have been more surprised if he had taken a gun, shot it at a piece of tissue paper, and what he shot came back and hit him. And the reason why it's so shocking, I always ask kids, are you shocked? Isn't that shocking? And they'll go, no. It's because he showed that the atom is empty space. So the only thing that stops this hand from passing through that hand is energy, not matter. Everything is empty space. Mind blown, right? So then Rutherford came up with what's called the planetary model of the atom, and it's what you think of as the Jimmy Neutron model of the atom. That he said that he thought the electrons orbited the nucleus. He realized that the nucleus was positive. Nucleus is Latin for little nut, and he thought that the electrons orbit the nucleus like the planets do the sun. He said there's patterns in nature. Maybe this is the pattern. Maybe they're like little solar systems. So you see that where you see that the electrons going around the neutron in those orbits. That's the planetary model. Okay, so let's see if we need to talk about anything about that. Okay, so where static electricity comes from is if you have something and you can rub the electrons off of it, and you can. If you blow up a balloon and rub it in your hair, then the electrons will get rubbed off, and your hair will have more electrons, the balloon will have less. Opposites attract, your hair will be attracted to that balloon. Now, when I first started teaching physics, decades ago, that I was reading, it said for a demonstration to have the kids do that, rub the balloon in the hair, and then put the balloon on the wall, and it will cling to the wall. And they said, and it'll just stay up there all year. Not in Georgia. Our air is too humid. It will immediately start crawling down the wall. It might barely cling for a second if it's a sort of dry day for us, but we are super, super humid here. We're between the Atlantic and the Gulf, and Georgia is an extremely humid environment. So I like it. I like living in Georgia, but we cannot do that experiment that they said because our charges will dissipate. Because if you remember from chemistry, and I think we even talked about in physics, that water is a polar molecule. It has a positive and negative end, and so therefore it dissipates those charges, those negative charges, or positive because the electrons have been rubbed off, and it neutralizes everything. Water just gets in there and neutralizes it. Okay, so talk about clouds. What causes, so it's rubbing the electrons off, will leave something positive, and what the electrons get rubbed onto is negative. And you can do that. Your book talks about you can rub a plastic comb with a piece of silk or wool. You can attract pepper with that. You can attract hole punch things. And that's one of the things I want you to do this week is I want you to do experiments with static electricity. I want you to go find them on YouTube, things you can do at home, because the lab in the book is a big old pain and you don't want to do it. I've done it, and I don't even like doing it with the right equipment, and you're not going to want to do it without the right equipment. I've bought the right equipment with taxpayer money before with physics, teaching in public school, and it immediately breaks. It's just frustrating. There are better labs out there that you can start play with electricity. Don't get shocked, but go play with electricity is what I want you to do for your labs. Go find some. Go look on the internet. There's plenty of them out there. There's lots of fun things to do with static electricity, and I'll tell you a couple as we're going through this that I want you to do. But I want you to go find some on your own too. So anyway, where does the lightning come from? Well, the wind in thunderstorms is what's rubbing the electrons off and causing static electricity. Usually, and let me make sure I get that one, yes, the bottom of the cloud becomes negative and the top of the cloud becomes positive. When that happens, then as the negative cloud goes over the neutral ground, the electrons that are on the ground will scoot away because lights repel, and the ground becomes positive, which looks very attractive to all these electrons up here that are negative, and lightning. Now, here's a little safety tip about lightning. Don't be outside in lightning, and if you are, don't go stand under a tree, because lightning is attracted to whatever is tallest and dome shaped. So if you're standing out in a field, your little domed head is going to be attracted to the lightning. It's going to hit you. If you go stand under a tree, that tree is dome shaped, it's going to be attracted to the lightning. The lightning will hit the tree, but it won't just hit the tree. If you look at pictures of lightning, it branches out all over. You're going to get fried too. A few years ago, there was a boy and a girl standing waiting on the bus, and their school to pick them up. They were waiting on their bus to get there, and they were standing under a tree, and the boy was tossing keys. Lightning hit the tree, the keys, he died, and the girl was fine. So you really never know with lightning. Lightning can strike anywhere, right? And it can even strike in the same place twice. That's a myth. You can tell that lightning strikes in the same place twice. If you go to Atlanta to Stone Mountain and go up to the top of the mountain, you will see these pock marks, these round circles on the mountain, and that's where lightning is struck at. And you will see where a big lightning struck, and then a little lightning struck, and there'll be another pock mark inside the same pock mark. So lightning does strike twice. That's a myth. It'll strike in the same place. So anyway, what if you're outside? One time I was outside. It had been raining, but it had cleared off, and I wanted to go out to my garden and pick some tomatoes for lunch. So I go out to the garden. It's not raining at this time, and I'm picking the tomatoes, and suddenly every hair on me starts standing on end, all my arm hair and stuff like that. I knew that I was about to be hit by lightning. So I immediately laid down in the mud in the garden, dissipated the charges, and it hit a tree right by me instead. Exploded it. It was one of those Bradford pears that just in my neighbor's front yard just it was back when we lived in Douglasville. So that's what you do. If you suddenly feel all of your hair on your arm or whatever standing up, lay down, dissipate those charges. Do not be the tallest thing on the environment. And also, you know, that's lightning, electricity travels through dirty water, not through pure clean water, but dirty water. So lakes, your bathtub, things like that. You want to not be swimming if it's going to lightning, because it can travel a long way and shock you. So and we'll talk more about electricity safety in the next chapter when we get to current electricity. Just I always try to bring out the safety stuff. So what is the difference in an insulator and a conductor? Conductors are things like metals that conduct heat and electricity well. Insulators are things like this insulation on these wires, this rubber. Wood is a good insulator. Things that don't conduct heat and electricity well. So graphite in your pencil does conduct electricity, and you can do an experiment where you sharpen both ends of a pencil, put leads on it, and you can conduct electricity through your pencil. That's a pretty fun little activity. Oh, so here's another activity I want you to do. I want you to get some Scotch tape and take 2 pieces and tape it down to your table or desk, whatever you've got, and then rip them up. And then it will cause the electrons to be ripped off, and then these will be charged the same. And as you bring them together, they'll repel from each other. Or then you can take 2 pieces of tape and do them together and rip them apart. One will be positive and one will be negative, and then you hold them together and they will be attracted to each other. So play with tape. It takes a little bit of work to do it the right speed of ripping it off. If you rip it off too fast, they curl up too much and they won't be nice where they can interact like that. So that's one of the ones I want you to do. All right, so there's some math that we will do. So come back for the math video and I'll go through with that. And that's pretty much it. Come back for the math video and we'll talk about the rest of this chapter. Like, share, subscribe, and remember, science is great.